The goal of this part is to, if you look at your Nexys4 DDR board, you'll notice 8 7-segment displays right above these switches. I'm going to pull this up so you can all see that. So we're going to memory map that so that we can write to it using our MIPS assembly or MIPS C code. So this is the process, and this is the general process for adding any kind of peripheral. So you want to add an SPI port, similar process. We add the hardware to drive, in this case, the 7-segment displays, memory map the digits and the enables, modify the interface to actually output that to the outputs of the FPGA, and connect it to the inputs of the 7-segment displays, and then run it. Okay, so let's look at this process. And the point of this process is so that, number one, to show you this one. It's useful to have the 7-segment displays, but you want a UART, or you want an SPI, or an I2C interface. Same process. Just so I mention it, so this module gives you the hardware for all of it. I give you all the Verilog modules and the code to show you how to do it. And the next module that you can do, when you get back to your university, you build the hardware yourself. It's for adding a counter, a millisecond counter. Okay, so let's add our hardware to drive the 7-segment displays. Quick review of 7-segment displays. There's 7 segments, A through G, and the display lights up according to what number we want to light up to display. So 0 lights up all of the outside digits, A through F. 1 lights up B and C. So one thing to note is that this is on the Nexys4 DDR board. They're low enabled, so they're low asserted, that is. So here's a Verilog module for the 7-segment display decoder. It takes in the number labeled data here, so the 4-bit value, 0 through 15, 0 through F. And for example, if it's a 0, that top line says the segments should be all zeros and only G should be 1. That means G is not lit up, right? All the outsides ones. So it's low asserted 7-segment display. All right, and this one, I've made it so that it can output any hex digit, so 0 through F. There are 8 of these digits, as we see here, 8 7-segment displays. There are several models that you could use for driving these. You could drive each of the digits separately, would have a segment A through G for all of the digits, and then so it would have 7 times 8 of those. Instead, we use the Digilant board and the Nexys4 DDR board use a slightly different scenario here. So we're going to connect all of the digits to a single 7-segment display input. So CA is connected to the A segment of all of those 8 digits. CB is connected to B, the B segment of all of the digits. And then we add another input, the enables, which are labeled AN0 for digit 0 through AN7. So in order to drive the 0th digit there, I need to drive the segments, CA through CG, to what I want to display, and then also drive AN0. And the enables, those AN0 are low asserted as well. So in order to enable the 0th digit, I have to make AN0 a 0. Okay. And then, for example, say I wanted to go ahead and display the value 0, I'd make CA, probably should have labeled it on the other one, but these are all connected by name. So CA through CG would be all zeros and a 1. All right, so it's a little bit different. Then the question is, well, I don't actually want to drive all the segments to either the same value or just drive 1. What do we do? Exactly, yeah, we time multiplex it and say, okay, first drive digit 0, then 1, 2, 3, through 7, and make it so fast that my eye can't tell that it's cycling through. So that's exactly what we're gonna do here. So for example, we're gonna drive each of them at 2 milliseconds. So we'll drive digit 0 to some value. In this case, we're driving it to whatever value we wanted to do. But AN7:0 only enables digit 0. So everything else is high except for digit 0. At time equals 2 milliseconds, now we enable that first digit, the one to the left of digit 0. Time equals 4 milliseconds, the third, and so on. So then the question is, well, how do I build hardware for that? Well, the first thing we're going to need to do is be able to store the value of the enables. So which ones do you want to have on? We can store that in a register called seg enable. Again, that _n means it's low asserted. And now we're going to need 8 registers to store the actual values we want to be able to output on those 7-segment displays on each of those digits. So we could have stored the segment values, CA through CG, but we can also just store the numbers and then put it through that 7-segment display decoder. So now we just have to store 4 bits for each digit instead of the 7. OK, so digit 0 we'll store in seg 0 _n, and digit 7 seg 7, and all the ones in between. OK, so we're going to need 9 memory mapped registers that the user can write to using a program. And then we're going to have a 3-bit counter that will multiplex through those. And first choose digit 0, digit 1, digit 2. And so if we turn over to the whiteboard over here, here's what this would look like. So we have this slow counter feeding this, a slow clock feeding the counter. The onboard clock is 62 megahertz, so just divide that down. And I ended up making it was actually just under 500 hertz, which is about 2 millisecond time period. So this count will then cycle through from, let's use a different color here. So we'll start at 0. At time t equals 0, this will output, it will select the seg 0 number, output that of this multiplexer. This is also driven by this 3-bit counter. We have seg enable n. So let's say we want to enable just the least significant 4 digits. Everybody see that? That's the least significant 4 digits enabled. But now I need to select, OK, I want to mask off everything but the 0th digit enable. So I do this or it with all 1s and a 0 to mask off that 0 here. So this will give me 1, 1, 1, 1, 1, 1, 1, 0. It will say, yep, that one's enabled, and go ahead and use it. OK, so then count 0, 0, 0, feeds this out to the enable pin, which will be fed to the enables on the Nexys4 DDR board. This one I don't feed, this number here, let's say it's feeding number 5. Let's say we want to display the number 5. We don't send that directly to our 7-segment display. We use that 7-segment display decoder that I just showed you. We'll then convert the number to the appropriate 7 segments, CA through CG. Okay. All right, so we'll do that one. At time t equals 2 milliseconds, this will increment, go to 0, 0, 1. It will now select this one. And that one, it will mask that one. 3, 4, and I'll keep repeating, refreshing those values every 2 milliseconds. We're going to go ahead and memory map the digits that we have. So we have the enable signal. That's this value. Map it to the next available memory address, hex BF8, 0s and 1, 0. And then we have the values that we're going to store to each of the digits. So we've gone through the first 2, added hardware to drive the 7-segment displays, memory map the digits, and now we need to modify the interface to drive the 7-segment enable pins and the values. OK, so here we modify the GPIO module, add an output that connects to these pins. So we have the enables, 7-segment enable N, and the actual CA through CG, which is IO 7-seg N. In the top-level module that is the Nexys4 DDR wrapper module, now we map those outputs, the IO 7-seg enable N and IO 7-seg N, to the anode, the AN signal, and the CA through CG. OK, cool. Now the last thing we need to do is say where these pins are, and that's in the Xilinx design constraints file that maps the name that we have. So in this case, CA, the A segment, will map to pin T10, just because that's what the PCB has that connected to. And the nice thing is, let me go ahead and open some of these files and show them to you. Here's our directory, MIPSfpga modules, and we'll go to the RTLUP that holds all the Verilog for MIPSfpga. So here we have all of our Verilog files and header files. If you scroll down, you'll see a bunch of files that start with MIPSfpga, and those are those higher level modules and the AHB module. Okay, so let's first open this 7seg decoder just to show you. This is that same file that I had shown a second ago in the slides. All right. And so you're going to see these Verilog files there, or I will give them to you in a moment. And all of these files, you'll notice MIPSfpga underscore AHB, those are all the ones associated with the AHB Lite bus, so peripherals and memories. So we'll start from the bottom with what we started with, the 7-segment display decoder. Takes in our number, data 3:0, and outputs the 7 segments, segment 6:0. All right. Now this is that timer that we had. This is the timer for multiplexing the values. So this receives as input the actual enable signal, EN, and the values of each display, of each digit, display 0 through display 7. Okay, so that's these values, display 0 through display 7. And now that thing that we're going to output, display enable out, is this value, that masked value. And display out will be the 7 segments that we want to display. So that's what we're going to connect to the board that connects to the 7-segment display. All right, so have these individual enable signals, enable 0 through 7. Those are those masked enables. Enable 0 is this one, enable 1, 2, 3, feeding to the multiplexer. Finally, we have a counter, a 17-bit counter that divides down the clock, and a 3-bit counter that's going to feed the multiplexers to choose which digit we're displaying, digit 0 through digit 7. And then the last thing we have is our 2 multiplexers for the segment enables and for the segment values. Okay, so the last thing that we do is we, from this segment value, you'll see num out. That's this value here, num out, connected to the input of our 7-segment display decoder. Then we get our actual 7 segments that we want. Display out, DISP out, that we're going to connect as the output of this module. Let's go ahead and look at our GPIO module. This is the picture that I showed on the AHB bus hanging off of there. So it has inputs, H clock, H reset, address, write data, H write, select, and read data. So those are the ones we expected. And now it has these memory mapped I/O values. These are the actual values that we're going to be sending to the output of the FPGA to drive either to receive the switches or push buttons, or drive the LEDs or the segments, 7-segment displays. All right. So here's our 7-segment timer instantiated. And now we're going to say, OK, let's go down here and say, if at the positive edge of the clock, if there's a write signal, H write is asserted, and I'm selected, that comes in from the address decoder. Now I want to figure out which one of the IOs am I trying to write to. The LEDs, some boards have green LEDs too, so that's where that second line is, but the first one's the only one we're using on this board. The LEDs, the 7-segment enable, or one of the digits, the value of one of the 7-segment displays. And then on the bottom, if it's not writing, we can then select which read data from the switches or the push buttons. That's done combinationally, because if we remember that multiplexer, it's not going to select it if it's not selecting from the GPIO module. And then we can look at the next module, which is this MIPSfpga AHB, which includes all of the the GPIO, RAM 0, and RAM 1. And if we look at this down here, we can see we have our reset RAM, which is holds the boot code. So RAM 0 is that top one. RAM 1 is what was in that figure for the next one, holds our program code, and now we have our GPIO module. The only thing we added were these outputs so that we could output the 7-segment display enables and value. And then we have our decoder and our mux. Anybody want to look at those modules? Yeah? Go ahead and look. OK. All right. So we instantiate it. Address decoder is down here. Basically, depending on, we're going to select module 0, which is the boot code, if we match the address. This could have said H address equals hex 1FC0 something. But all we need is those top bits to match on. Generate the select signals H select 1 and H select 2, depending on the address. And the multiplexer is just about as simple. Using the select lines, H select, I'm going to read the data from either module 0, 1, or 2. Okay, so just in Verilog code, what we saw in that figure. Okay, and then the last thing that we're going to do is we're going to keep going up the levels of hierarchy and now instantiate the H being the system. So in fact, I'll just look at the top level module. Here's the MIPSfpga Nexys4 DDR. That's our wrapper module. Go ahead and look at that. And here are the inputs. We have clock and reset. And then we have our push button switches as inputs, and LED, our enable for 7-segment displays, and the 7 digits for the 7-segment displays. Instantiate the system and map those to those outputs, IO 7-segment N and IO 7-segment enable N. And that's it. Now we can go into Vivado. If you haven't done it before, you can follow what's in Module 1. It describes the details of adding the Verilog code, adding the constraints file to your project, compiling it, synthesizing it, and then downloading it onto the board, which we've done the last part. But if you want to go through that first step, once you start modifying the code, now you have to compile and synthesize, which can take some time, 10 to 20 minutes. So not something you're going to be doing, oh, I made a small change, right? You want to be able to test your individual modules first, and then put it into the larger system. That's also part of the real world perspective of it. It's a real system that's going to take some significant time to both simulate and to synthesize. Okay, so then we can go ahead and run programs on it. Let me show you the program. I have one written for you here. If you go to your usual place, MIPSfpga modules, and now open the fourth. Go to the docs. Let's open we don't need to go to the docs folder. Let's go to the module 4 7seg, C example, and you can open main.c. I have examples in both C and assembly. But now that we have this hardware to support it, we just say where those addresses are. Hex BF8 ... 1014 through 30. And now we can write values to each of those segments in the same way that we wrote values to the LEDs last time, just a different address. And the nice thing is I can write the enable. So the first one, this IO 7seg enable equals 0, enables all of them. If I wanted to just enable one of them, I'd write hex FE equals hex FE, or half of them equals hex F0, or whatever. But I don't have to worry about the multiplexing. I've built the hardware behind that to do it. So I can enable them, and then just write values to them. And this hardware figures out how to cycle it through every 2 milliseconds. All right, so that's it. I kind of walked you through that. That's the first half of this. Actually, most of this module describes what we just went over. But you can review that. This is module 4. I'll pass this out now.